All right, in today's lesson, we're going to be exploring the concept of work from a physics standpoint, from a standpoint of mechanics. Okay, we have an idea, I'm sure you know, work is used in everyday language, okay, doing something, get your work done, that kind of thing. But when we're dealing with the study of mechanics and physics, work is something quite different. Work is defined as an energy transfer. So it is a transfer of energy into or out of a system. So if we have a system here, if E is energy, energy can be transferred into a system by work, or work, conversely, can transfer energy out of a system. Okay, so work is a transfer of energy, and basically the way this energy is transferred is through the action of a force on an object. So again, it comes down to forces, and when we're talking about forces, we're essentially talking about any force. Any force can do work. Okay, provided certain conditions apply. Okay, but any force does work in our view here. So the very simplest definition of work is that work, and we use capital W for work. Work is equal to force multiplied by displacement. So for work to be done, there's two constraints. Number one, there has to be a force acting on an object, on a system. And number two, that system has to move, displacement. Okay, displacement cannot be zero. So if displacement is not equal to zero, therefore an object moves. So there has to be a force causing an object to move, and if that happens, that force does work on a system, either transferring energy in or out. Okay, so some examples of forces that are working or not working. So here, number one, we look at the shelf. The shelf is at rest, so no work is being done. Delta V equals 0. Number two, the person pushing the cart. Okay, so F is applied here. The cart moves, delta D. So there is work being done because there is movement in the direction of the force, i.e. a displacement. So example number two, the force is doing work. If we are going counterclockwise, example number three, we can see there is a cable here attached to a log. Now the tractor is moving in the X, so delta D is in the X. If we look at a free body diagram here, we see that there's a force at an angle. So we've got Fx and Fy. Fx would be parallel to the displacement of the tractor. Therefore, Fx does work, or in other words, the horizontal component of the force. Okay, so this would be, example three would be a two-dimensional example of work, which we'll get to. Okay. Example number four, we have circular motion, we have tension. Okay. So tension is causing that centripetal force, but the object is moving in the circle, and there is a right angle, 90 degrees, between the movement, or the delta D, and the force, so therefore there is no work being done. So the tension in the string is not working, as there is no movement in the direction of the force. That ball is not moving in, it's moving, okay, tangent to the circle made by the tension in the string, so there is no work being done. Okay, there is no work being done because F would be perpendicular to delta D, therefore zero work. Okay, so those are some examples of forces that do or do not do work. So again, very important point. If a force is applied and there is no displacement, there's no work being done. So work can only be done if the object moves. The object is displaced, the object moves. Okay. Another example, we have the weightlifter holding the weights in place. There's no work being done here because the weights are not moving up or down. There's 0 delta D, so therefore there's no work being done. So again, I think that work is a result of a force applied over a distance, F times delta D. Okay, so we need a unit for work. So work is transfer of energy, so it has an energy unit. So work has an energy unit, and that is the joule. Okay, and so if work equals F times delta D, that will be a Newton times meter, or a Newton meter. That is defined as 1 joule. So 1 Newton meter is defined as 1 joule. Work is a scalar quantity. So moving on. Some examples of calculating the work done for a one-dimensional force. Again, work is defined as F delta D. So we need to know force, we need to know displacement. If we don't know displacement, maybe we can find it using kinematics. There's other examples like that. We'll work from the beginning and begin with some simpler examples. Okay, so example 1. Calculate the work done by applying a force of 850 newtons east on a 3,500 kilogram car to get it to move 150 meters east. So we should list what we know and what we don't know and go from there. So we know that the force applied, F, is 850 newtons. We know the mass of the car is 3,500 kilograms. And we also know the delta D. The delta D is 150 meters east. So the simplest definition of work is work equals F delta D. We know both, so it's a matter of multiplying. So 850 newtons times 150 newtons. They're both in the same direction. Okay, so that was east. And so multiply 850 times 150. And we get 127,500 joules. 127,500 joules. And that would be our answer. Okay. Simplest example, but that's how we work with work. Okay. Second example would be we don't know delta D, but we have some kinematic information that we can get. So calculate the work done by applying a force of 20 newtons to a 0.4 kilogram puck as it slides along a frictionless surface from rest 10 meters per second in 0.2 seconds. Okay. So work equals F delta D. We know force is 20 newtons. We know the mass of the puck is 0.4 kilograms. We could find the acceleration if we wanted to. We could go A equals F over M. Okay, but we'll see if we need to do that. V1, we know the initial velocity is at rest, so it's 0 meters per second. We know V2 plus 10 meters per second. And we know delta T is 0.2 seconds. So if we think back to kinematics, we know V1, we know V2, we know delta T, and we want to find displacement. Okay, we can find displacement using kinematic equation number 3. Delta D is 1/2 times V1 plus V2 multiplied by delta T. So we can go ahead and figure that out first. So 1/2 times 0 plus 10 times 0.2 seconds, and we can get our delta T. So 0.5 times 10 times 0.2 is 1 meter. That works out very nicely. So now work equals F delta D. So that will be 20 newtons times 1 meter, which would be plus 20 joules. Sorry, correction. Okay, so that would be 20 joules. So that is an example where we had to use kinematics to get delta D, and then figuring out the work from there. Okay. Moving on. Number 3. Calculate the work done by lifting a 65 kilogram outboard motor a distance of 1.4 meters from the ground up to the box of a pickup truck. Okay. So essentially we've got the ground, we've got this motor, we're lifting it up. Delta D is 1.4 meters. With the force, we don't know what the force is. So if we think about it, the outboard motor would have its weight pulling down, Fg, and to actually pull up the motor, pick it up and move it, lift it up, you would have to apply force opposite, so you have opposite to the weight. So the force applied in this case equals Fg, which equals mg, and we know m, and we assume it's on Earth, so we would g. So that would be 65 kilograms times 9.8 meters per second squared, the acceleration due to gravity. And we can figure out the weight of the outboard motor, 65 times 9.8. We get 637 newtons. Okay, so that is the applied force that would be needed to lift the outboard motor. So work equals F delta D, that would be 637 newtons times 1.4 meters. We're going to get our answer very easily. We take 637, which we calculated, times 1.4, you get 891.8. So the answer would be work equals 892 joules. Okay, so 3 basic level examples of exploring the work done by a force. Again, work equals force times displacement. Okay, so we know that most forces are not one-dimensional, they are mostly two-dimensional. So how do we deal with a 2D force? Well, if we have our force that's being applied, F, okay, we know that there will be 2 components. So if we're going to consider an object sliding forward, delta D, all right, instead of talking about X and Y, we're going to talk about parallel or perpendicular to the displacement. So if this force here is being applied, okay, there's going to be 2 components. There's going to be the parallel component, okay, F parallel, and there's going to be the perpendicular component, okay, and it'll be your angle theta. So note, F parallel does work, okay? So F parallel would equal F times cos theta. So we can essentially substitute that, okay, into our work calculation. So work, whoops, backing up. Again, just so we don't get confused, why is it cos theta? Because of course it's the adjacent side to theta. So dealing with the 2D force, we know that work equals F delta D we can write it as F cos theta times delta D, and that would be our formula. Typically, it's written as this, F delta D times cos theta. It doesn't really matter where you write it, but that would be the work for a 2D force. Okay, so we can begin then. Calculate the work done if a child pulls a wagon 9 meters with a force of 350 newtons at an angle of 38 degrees to the horizontal. So we have our free body diagram. Here's our F. We want our F parallel, which equals F cos 38. So work will equal F cos theta times delta D. So 350 cos 38 times 9 meters. Make sure we're in degrees. So 350 cos 38. And we'll multiply that by 9 meters. And you get 2,482 joules. Say figs, we need 2. So our final answer for work would be 2,500 joules. Okay, so hopefully that is a straightforward example of a force applied at 2 dimensions. Okay, so now we talked about work being a scalar, so it has no direction, but work can have a positive or negative value. And this does not imply direction. Okay, what we're talking about of positive versus negative work essentially is this. Again, when we have a system, okay, remember energy transferred is work done. So energy can go into a system or energy can come out of a system. So if energy goes in, positive work is done. If energy leaves the system, then negative work is done. So that's pretty much how it works. If a system has positive work done on it, its energy level increases. If a system has negative work done on it, then it has energy leaving the system. So what does this mean in terms of the force? Well, if we have these 2 examples, A and B, you'll notice that the block is moving forward to the right, speeding up. Force is parallel to delta D. In example 2, force is anti-parallel to delta D. So when a force is parallel to the displacement, that is positive work being done. If the force is opposite to the displacement, that will end up being negative work being done. Because of course, the angle between delta D and the force would be 0, and cos 0 is +1. In the second example, you'll notice the force is opposite, so it would make a 180-degree angle. So that would be cos 180, which is -1. That's why 1 is positive and 1 is negative. So the component of the force in part A is in the same direction, therefore the work done is positive. Likewise, the component of the force in B is opposite, and the work done by that force is negative. Okay. So what does negative work look like? Typically, things that do negative work, big example would be the force of friction. So a car rolls to a stop from an initial velocity of 25 kilometers per hour over a distance of 125 meters. The mass of the car is 1,200 kilograms. Calculate the work done on the car by friction. So if we look at a free body diagram, if the car was moving forward, delta D, the force of friction would be in the opposite direction. Therefore, it does negative work. So how are we going to find the force of friction? Well, if the only force acting on this object is friction because it's rolling to a stop, okay, then force of friction must equal F net, which in this case would equal MA. And so we know the mass of the car, 1,200 kilograms. We don't know A. So if we find acceleration first with kinematics, then we'll be in business. Our unknown is acceleration. V1 is 25 kilometers per hour, which we'll have to convert to meters per second by dividing 3.6. V2, if it rolls to a stop, is 0. And we know delta D is 125 meters. So this leads us to kinematic equation number 5. 2A delta D equals V2 squared minus V1 squared. So V2 squared is 0. So acceleration will be negative V1 squared divided by acceleration double. So we have 25 kilometers per hour divided by 3.6. We'll square that because I don't care what that number is. And then we'll divide that by 2, whoops, that's not 2A, 2 times displacement. So 2 times 125 meters. You can figure out the acceleration of the car by friction. Okay. So we'll take 25 kilometers an hour divided by 3.6, and then we'll square it. And then we'll divide that by 2 times 125. And you get 0.192901. So 0.1929 will be good enough. So 0.1929, and it's negative direction, meters per second squared. So if the acceleration is negative, that obviously means that the force applied is negative. That's going to lead us to friction doing negative work. So now we can go and find the F net. F net is MA, 1,200 kilograms times 0.1929. That's negative. So we can get our answer. So we take that and times it by 1,200. And you get 231.481. Newtons, and that's negative. Sorry, and that's force of friction. Okay, so we've got our force of friction from our acceleration, right? Simple dynamic situation. Now we can calculate the work done by friction. So the work done by friction is going to equal F delta D. So that's negative 231.481 newtons. And I believe it rolls to a stop over 125 meters. So our delta D is 125 meters. And we can get our answer there. So we take the 231, and then we multiply that by 125 meters. The work done by friction is 28,935 joules. 28,935 joules. 28,935 joules. It's negative because of friction. And to our final answer, the significant digits. We need 2 sig figs. So it would be negative 29,000 joules would be equal to the work done by friction when the car rolls to a stop. That is an example of calculating negative work. Another way we can find work is if we plot a graph of force versus displacement, force on the y-axis and displacement on the x-axis. Essentially, this is very similar to what we did last year with our position time graphs and velocity time graphs, but the work is the area underneath the F delta D graph. If the area is above the x-axis, that is positive work. And if the area is below the x-axis, that's considered negative work. If a variable force or a non-constant force acts on the object, then the graph would be a curve, and determining the area would require the use of calculus methods. And so we will assume a constant force applied, and thus we will not be examining variable forces in grade 12 physics. So if we're given a graph, here we have displacement, delta V, force F. You can see that we have these line segments. So even though the forces are different, they're constant, okay, or they're changing in a constant manner, and thus we have these straight line segments. Okay, so again, we're talking about area of shapes. So if we've got a square, that's going to be length width. If we're going to have a triangle, 1/2 base height. And if we're going to have a trapezoid, that's going to be 1/2 A plus B times the height of the trapezoid, where this would be H, A and B would be the two parallel sides. Okay. So now all we have to do is figure out what our intervals are for the distance, okay, and then calculate it accordingly. Notice that this graph is all above the x-axis, so everything is going to be positive work. The only way it would be negative work would be if the line went below the x-axis. So example 1, calculate the work done from 0 to 3 meters. Okay, so we need to find the area. So 0 to 3, all right, is that shape there, which is a triangle. Okay, so that's 1/2 base times height. So the base, okay, would represent the 3 meters, and the height would represent 3 newtons. So 3 meters times 3 newtons. Whoops. Messy. That'll be 1/2 times 9 Newton meters, which would be positive 4.5 joules. So positive 4.5 joules of work were done from 0 to 3 meters when that object slid that distance. Okay, the next example is from 0 to 5 meters. So again, we need to find the area, and I'll just erase what we did here. Okay, and we'll do a new color, 0 to 5 meters. Okay, so 5 is here, so it looks like that is our shape there. We'll outline the shape, and you'll notice that we have a trapezoid. So that is side A, that is side B, and that would be the height. And A and B are the parallel sides. So the area is 1/2 A plus B times height. So B would be 5. A, okay, we'd go 5 minus 3. So A would be 2, B would be 5, and the height would be 3. And A and B is the meters for displacement, and height is the force in newtons. So the area would be 1/2 A plus B times height. So 1/2 A, which is 2 meters, plus B, which is 5 meters, times the height, which is 3 newtons. So that's 1/2 times 7 meters times 3 newtons. That would be 1/2 times 21 Newton meters. And you get positive 10.5 joules. And that would be an example of calculating the work done from 0 to 5 meters using the information from the graph. We can put it all together in example 3 and find the total amount of work done. So the delta D total would go from 0, I believe it's to 10 meters. So essentially what we'll have to do is divide this into workable shapes. So 0 to 10 meters. So we will find the work done in sections of the graph and add them. Okay, so we already know the work done from 0 to 5 meters. We calculated that in example 2. That was positive 10.5 joules. We don't need to recalculate that. Okay, so we already have this. Okay, so essentially what we have left are a few other sections. This is a trapezoid, so we've got 5 to 6, then we've got 6 to 8, and then we've got 8 to 10. Okay, so we have a trapezoid, we have a square, rectangle, and we have another trapezoid. Actually, we have to divide this into 4 shapes. Okay, that's 9. So we have a trapezoid, rectangle, trapezoid, rectangle. So there's 4 more. Okay, so that we'll have to do. So we have 4 sections and 4 shapes to do. Okay, so we've got 5 to 6. Six to 8, 8 to 9, 9 to 10. Okay, so it's going to be 1/2 times A plus B times height. So we can kind of speed this up here. A and B are vertical this time, so A is 3, B is 2, so A plus B is 5, and the height in this case is the meters, 1 meter. So that would be 3 plus 2, 5, and then that would be 1. So 1/2 times 5 newtons times 1 meter. Okay, 6 to 8. It's length width. So the length would be, in this case, 2 newtons, and the width would be, 2 meters. 2 meters, and this would be 2 newtons. So 2 times 2. So that would be 2 newtons times 2 meters, again, because this is a trapezoid, and this is a square, and here another trapezoid, and then we have a rectangle. Okay, so our second trapezoid from 8 to 9 meters. Okay, so A and B. So A would be 2 newtons, B would be 5. So that 2 plus 5 is 7. So 7 newtons for the A plus B, and the H would be 1 meter. So the 8 to 9 would be 1/2 times 7 newtons times 1 meter. And lastly, the rectangle from 9 to 10. The length would be 1 meter, and the width would be 5 joules. So 1 meter times 5 joules. And now we can figure out the areas, and we won't forget to add the first one. So 5 times 1 is 5 times 1/2 is plus 2.5 joules. That would be plus 4 joules. 7 times 1/2 is plus 3.5 joules, and plus 5 joules. So now the total work done would be the sum. 10.5 joules plus 2.5 joules plus 4 joules plus 3.5 joules plus 5 joules. Add all that up. The work is all positive. That's why I emphasize with the extra pluses inside. And we can get our answer. Okay, so 10.5 plus 2.5 plus 4 plus 3.5 plus 5 gives us 25.5 joules. So positive 25.5 joules of work done in total when the object moves from 0 to 10 meters. So this example would be looking at calculating the work done if we have a force displacement graph. So this concludes the introduction lesson on work, and you can practice the practice questions that are on the website that were uploaded as well. And we'll be moving on next, looking at energy and what it is, and then how energy and work are related to each other.